Hello and welcome to the session of Power Electronics. Today's topic of discussion is single phase half wave control converter with inductive load and freewheeling diode. So this is in continuation with our previous session. So if you missed the previous session, the link is provided in description box. Please go through it. Now the outline of today's discussion is we are going to understand the working of the circuit in positive half cycle as well as in negative half cycle. Then we are going to understand the effect of freewheeling diode, then try to plot the output waveforms, then finally going to derive the DC voltage for this, and we are going to compare the DC load voltage condition for resistive load, for inductive load and inductive load with freewheeling diode for different firing angles. Now what is freewheeling? Freewheeling is nothing but ability to allow anything to pass through it freely or without any opposition or without any restriction. So that is a freewheeling. Without any freely allow energy to pass through it. So the diode is named as freewheeling diode because it is allowing the energy to freely pass through it. Now freewheeling diode is also known as a flywheel diode as well. Now we are going to understand. Let's look at the circuit of this particular discussion. So circuit comprised of a 230 volt 50 Hz AC supply that is connected through a step down transformer to a half wave control converter circuit, which is connected in series with the inductive load, and a flywheel diode is connected across the load. Now the circuit, the SCR used in this circuit is having a forward breakdown voltage value very higher than maximum value of the supply voltage. Now as we are having an inductive load, obviously it will shows the inductive effect. Now inductive effect is nothing but the current will lag the supply voltage waveform, or we can say the voltage will lead the current waveforms. So if you like to understand this in detail, it is described with our half wave rectifier, half wave control converter circuit with inductive load. So please go through that. Now freewheeling, the idea of adding a freewheeling diode is to reduce the negative voltage that is developed across the load. Now what happens with this particular voltage? Now as we know that the DC is also known as average. So as the SCR is conducting positive as well as in negative half cycle, a positive and negative voltage will get developed across the load. And if we like to calculate the average, now the negative voltage gets subtracted from this particular positive voltage, and suddenly the average value across the load get decreases. So the same circuit which is providing a higher efficiency with the resistive load, suddenly the efficiency get decreases due to the inductive nature because we are getting a negative voltage. So for same firing angle, the resistive with the resistive load we'll get a more DC voltage, whereas with the inductive load we get a less DC voltage because of this effect. So we try to minimize this effect by adding a freewheeling diode, and that's why we have added this. Let's start with the positive half cycle. Now positive half cycle, let's say 230 or 50 Hz AC supply is applied, and if positive half cycle is available, that makes P1 as positive, P2 as negative. This induces voltage drop across secondary, that makes S1 as positive and S2 as negative. Now this will forward biases the thyristor T1 but reverse biases the freewheeling diode, but both of them remains in off condition. So as the gate pulse is applied, so at the instant alpha, as soon as gate pulse is applied, forcing the T1 to goes in on condition. As soon as thyristor T1 goes in on condition, it produces a load current with a path S1 T1 RL or through inductor through S2, through which it will be grounded, and because of that it develops a load voltage. Now as we know, as the load is of inductive nature, obviously the supply voltage and load voltage will be in phase, but the load current will lag the supply voltage waveform. Means that when the supply voltage reaches to the maximum value, the load current will be at the minimum value, and when supply voltage and load voltage reaches to the minimum value, the load current will reach to the maximum value. We'll try to observe this by using a graphical manner. So let's say a supply voltage is of sinusoidal nature. So at the instant alpha we have applied a gate pulse. As soon as gate pulse is applied, it forces the SCR to goes in on condition. So now because of that, a load voltage will get developed as well as load current will get established. Now as we discussed that the supply voltage and load voltage will have the same nature, so they will be in phase, but the current will lag the voltage waveform. So as we can clearly see, when the supply voltage and load voltage are maximum, the load current is minimum, so it is gradually rising to its maximum value. And when supply voltage reaches to the minimum value, obviously load voltage reaches to the minimum value, but the load current will be at the maximum value. So for the that is what is the inductive effect, in which we will observe a phase difference between load current and load voltage. So at the instant pi, what we have observed, at the instant pi, the supply voltage is at a minimum point. Because of that, load voltage reaches to the minimum value, but the load current will be at the maximum value, which can keep the SCR in on condition. So from alpha to pi, the current will be carried by the thyristor T1. Now let's go for the negative half cycle. Let's see what will happen in the negative half cycle. So now a negative half cycle is applied. If a negative half cycle is applied, that makes P2 as positive, P1 as negative. This induces voltage drop across secondary. That makes S2 as positive, S1 as negative. Now this will reverse biases the thyristor T1, but forward biases the freewheeling diode DF. So as freewheeling diode is in forward bias condition, automatically it goes in on condition. As soon as freewheeling diode goes in on condition, it applies as soon as freewheeling diode is in forward bias condition, it applies all the negative voltage across SCR. So all the negative voltage will get directly applied across SCR, which will reverse biases the SCR. Also, as freewheeling diode is in forward bias condition, it takes up all the inductive current through itself. So all the inductive charges will be bypassed now through the freewheeling diode. So it reduces the current flowing through the SCR below a holding current value. So as the freewheeling diode is in forward bias condition, it does two things. First, it applies a heavy reverse voltage across SCR because of we are in negative half cycle. Second, it takes up all the inductive charges which are flowing through the SCR through itself, and because of that, it reduces the current flowing through SCR below holding current value. So by naturally, it forces the SCR to goes in off condition. Now, as we understand with the inductive effect, the current continue to flow in same direction, but now current continue to flow from RL L through freewheeling diode and through RL again. So through that, all the charges will be removed. Now, as freewheeling diode is in forward bias condition, forward bias condition, it forces the T1 to goes in or thyristor to goes in on off condition. So as thyristor is in off condition, so our circuit the supply gets disconnected from the load. So as supply gets disconnected from the load, no load voltage will get developed due to the supply. As SCR is in off condition, so this is acting as an open circuit. So supply cannot deliver any voltage across the load, and during negative half cycle, no voltage will get developed across the load due to supply. So we'll observe that because of freewheeling diode is in forward bias condition, no load voltage will get developed, and all the inductive current will be bypassed to the freewheeling diode. We'll try to observe this by using a waveform. Let's look at the waveform. So this is what we have discussed for the positive half cycle. At the instant pi, as soon as negative half cycle is applied, freewheeling diode will be in forward bias condition. As freewheeling diode is in forward bias condition, applies the reverse voltage across SCR, forcing it to goes in off condition. So at the instant pi, the freewheeling diode commutates the thyristor T1, forcing it to goes in off condition. As T1 goes in off condition, the supply get disconnected from the load. So as supply and load are disconnected, no negative voltage will get developed across the load, and the current continue to flow through the freewheeling diode. So as we have discussed, from alpha to pi, the load current was carried by the thyristor, whereas from pi to till all the inductive charges are removed, the current will be carried by the freewheeling diode. So this is what we can observe from this waveform. Let's go further. What will happen? So the once all the inductive charges which are trapped across the load are completely removed, the current decreases. The load current will become zero. As soon as current flowing through the freewheeling diode decreases below becomes zero, it forces the freewheeling diode to goes in off condition. So at the end of this cycle, the SCR goes in off condition at the instant pi by naturally. So because of that, it disconnects the supply from the load. So no negative voltage will get developed across the load due to the supply, obviously. Now once all the inductive charges are completely removed, then freewheeling diode can goes in off condition, and finally at the end around let's say once all the inductive charges are completely removed, the freewheeling diode. So at the end of this cycle, SCR is in off condition, diode is in off condition, no load voltage, no load current. Now that is what we have discussed with the previous cycle. So from alpha to pi, the current was carried by the thyristor, and from pi to removal of all the charges across the load, the current was carried by the freewheeling diode. So we try to understand this by using the output waveforms as well. So let's start with the output waveforms. So let's we are going to plot the output waveforms for supply voltage, then gate voltage, load current, load voltage, load current, voltage drop across SCR, and current flowing through the SCR. So let's start with the positive half cycle. If positive half cycle is applied, now SCR is in forward bias condition, but as gate pulse is absent, it remains in off condition. And as SCR is in off condition, no load current, no load voltage, obviously no current flows to the SCR. Now at the instant alpha, as soon as gate pulse is applied, it forces the SCR to goes in on condition. So as we can discuss, as we can observe from this, as at the instant alpha, as soon as firing pulse is applied, it forces the SCR to goes in on condition. As soon as SCR goes in on condition, it jumps to a lower impedance state or lower potential state, as you can see from the waveform. As soon as SCR goes in on condition, it establishes a current, and because of that, load voltage will get developed. Again, the supply voltage and load voltage will be in phase, but the load current will lag the supply voltage waveform. So load current will be maximum when the supply voltage and load voltage is a minimum. So at the instant pi, as we can clearly see, the current is maximum, but the supply voltage and load voltage becomes minimum. Now after this, as we have discussed with the inductive load, the SCR remains in on condition because of current flowing through the SCR is still at higher than the holding current. So as we have discussed, let's observe for the negative half cycle. As soon as negative half cycle is applied, now we know that after the instant pi, the freewheeling diode is in forward bias condition, so it applies a reverse voltage across SCR. Second, it takes up all the inductive current through itself. So as you can see, sharp fall of thyristor current. Thyristor current immediately reduces to the zero or decreases below its holding current value. As also freewheeling diode is in forward bias condition, so it applies a reverse voltage across SCR, forcing it to goes in off condition. So freewheeling diode applying a reverse voltage, forcing the thyristor T1 to goes in off condition. So at this particular point, thyristor goes in off condition. Now even if we apply a gate pulse in during negative half cycle, SCR is not goes in on condition. So let's again go for the positive half cycle. Again, positive half cycle is available. Again, SCR thyristor is in forward bias condition, but as gate pulse is absent, it remains in off condition. As it is in off condition, so no load current, no load voltage. Let's go for the firing pulse. So if we apply a firing pulse at the instant 2 pi plus alpha, as soon as gate pulse is applied, again a load current will be produced and load voltage will get developed. SCR jumps to a lower potential state, producing a current. Again, at the instant 3 pi, we reaches to a crossover point at which supply voltage becomes 0. Because of that, load voltage becomes 0, but load current still at the maximum point, which can keep the SCR in on condition. But we know that case it doesn't remain in on condition. So during negative half cycle, again it applies the freewheeling diode will be in forward bias condition, which applies a reverse voltage across SCR. Also, it takes up all the inductive current through itself. So quite naturally, it reduces the current flowing through the SCR below a holding current value, forcing it to goes in off condition. So negative voltage as well as current reduces to below holding current value, forcing it to goes in off condition. So this is what we have observed with this. Even if we apply a gate pulse, SCR is not goes in on condition. So as we have discussed with the waveform, so from as we can observe for the load current, from alpha to pi, the load current will be carried by the thyristor T1, whereas from pi to till the removal of all the inductive charges, the current will be carried by the freewheeling diode. So that's what we have discussed. Now let's compare the waveforms with the inductive load. So load voltage of inductive load and the voltage drop across thyristor for the inductive load we have added with this. Now we can clearly observe that during negative half cycle, the SCR is continue to conduct. So as you can compare the two waveforms, the thyristor with inductive load continue to conduct up to the instant beta. So because of that, it helps to develop a negative voltage across the load. And as negative voltage gets developed across the load, as I mentioned in the start of this particular working, the DC is average nothing but positive half cycle or whatever the load voltage, the average of load condition. So average of positive half cycle as well as negative half cycle. So once we add the negative values in positive half cycle, so average gets decreases, and because of that, for the same firing angle, we get a lesser voltage with resistive load and with the inductive load. So as you can go for the inductive freewheeling diode, there is no effect of inductive load. As you can observe the load voltage waveform, Even we are in the inductive load, there is a no negative voltage developed, so we restore the DC voltage value as that of resistive load. So we make the circuit independent of the load condition. Even if it is a resistive load or inductive load, so still we will get the same voltage for the say for any firing angle. So this is what is this comparison is telling about. Now what we are interested in, we are interested in calculating the DC voltage across the load, and again DC is nothing but average. So keep in mind, what is the effect of freewheeling diode? Freewheeling diode minimizes the effect of, yeah, or minimizes the inductive nature or inductive effect of load, and because of that it restores the load voltage condition. And this is what is the key thing which we like to take from the working of this particular circuit. So let's try to derive the VDC. Again, VDC is same as the resistive load. So DC load VDC, the derivation of VDC is just like the resistive load. There will not be any change with that. So I am going bit faster with that. So VDC, again V of average. So it is nothing but area under one complete cycle divided by base. Our cycle positive cycle start from 0 to 2 pi. So our end starting point is 0, ends on 2 pi. So my base, as I mentioned, starting point, ending point and minus starting point. So 2 pi minus 0, that gives me the base as 2 pi. Now how to calculate the area? For an instantaneous signal, the area can be calculated by applying an integration from starting point to the ending point. So we are going to perform an integration for this entire range. So this is what is our load voltage waveform, at which we like to calculate the DC voltage, and we like to perform integration from the from 0 to 2 pi. So let's start with the integration to calculate area. Integration from 0 to 2 pi over the load voltage for an omega t. Now from the waveform we can say that there are three different values of load voltage, from 0 to alpha, and from pi to 2 pi we have a load voltage value as 0. So no load voltage get developed during this interval. And from alpha to pi we are getting a sinusoidal nature, as our input is sinusoidal, so obviously the output will again follow the sinusoidal nature. So again, so we need to split the interval, split the integration three parts, because load voltage is having three different values. So integration will be from 0 to alpha, alpha to pi, pi to 2 pi. Now let's substitute the value of load voltage in these. So the value of load voltage from 0 to alpha is 0, from pi to 2 pi again it is 0, and for alpha to pi the value is Vm sin of omega t. So let's solve it further. As we can see, as we understand, integration of 0 is 0. So because of that, the output, the value of these two equations will be 0. Now integration is not applied over Vm, so we are taking Vm out of the integration. So as integration is over omega t, so it will be applied over sine only. Now we know that integration of sine is minus cos, so that's why we have substituted integration of sine is minus cos of omega t over a limit alpha to pi. Now let's take out a minus sign out of this to simplify it. It is not necessary to get the minus sign out, but for simplification we can do it. If somebody don't want to take it out, you can keep it over itself. So so I have taken minus sign out of this. Now let's put the upper limit and lower limit. So upper limit minus lower limit. Cos, the upper limit is cos of pi and lower limit is cos of alpha. So we have substituted the both of values. Now cos pi, the value of cos pi is minus 1. So we have substituted the value of cos pi as minus 1. So minus of Vm minus of 1 minus cos alpha. Now let's try multiply minus of minus sign in the interval. So that gives you area is equal to Vm 1 plus cos alpha. So we have secured both area as well as base. So let's substitute in the equation of VDC, area divided by base, Vm 1 plus cos alpha divided by 2 pi. So this is the same equation as we have derived for the resistive load. So if you try to go for different firing angles, let's say alpha, if you substitute the value of alpha as 0, cos 0 is 1, so again we'll get the value as Vm by 2 if the value of cos 0 is 1, so 1 plus 1, that gives you 2 Vm by 2 pi, that gives you Vm by pi. That is the voltage same as half-wave rectifier. Now again if you substitute the value as pi by 2, cos of pi by 2 is 0, so that gives me the value of Vm by 2 pi. Now cos pi is minus 1, 1 minus 1 0, so that's why DC voltage becomes 0. So as we can observe from the waveform as well, as the firing angle increases, the value of VDC decreases. As you can see, maximum, half of that, and 0. So as firing angle increases, the DC voltage decreases. So this is what we have observed. So let's compare the three circuit, and then we can actually understand what happens with the inductive load. So the same circuit, single phase half wave control converter circuit with three different load conditions: resistive load, inductive load, and inductive load with freewheeling diode is compared. Now you can clearly observe these two equations are same, means even when we add a freewheeling diode, it makes the circuit independent of load conditions. So as you can see, for the firing angle 0, 90 and 180, we are getting the same voltage, whereas with the inductive load, as I mentioned, we are getting, it is working in rectification as well as in inversion mode. For 0 it is giving positive maximum, whereas for 180 it is giving a negative maximum voltage. So this is what is a difference that we have discussed in the working, its working as well. So we can compare on the basis of modes of working. So resistive load, with the resistive load, the circuit works in rectifier mode, whereas in freewheeling diode, same, it works in rectification mode. Whereas in inductive load, it was working with rectification as well as inversion. So let's summarize what we have learned. So we have discussed the working of single phase half wave control circuit with resistive load, inductive load, and flywheel diode, and or freewheeling diode. We understand that when we add a freewheeling diode, actually it reduces or it minimizes effect of load or inductive nature of load. So this is because of that, the voltage will be restored, will get the same value as that of resistive load. So with the inductive load and freewheeling diode, we are getting the same voltage value as we have observed with the comparison table. Freewheeling diode is basically used across many electrical and electronic circuit to reduce the inductive effect. As you can observe with the electronic relays or DC motor driver circuit, we generally use the diode or semiconductor diode in reverse bias nature, so that it reduces the inductive effect. So these contents I have taken from our book Power Electronics, Singh and Kanchandani. The page numbers are also mentioned, and thank you for listening this session patiently. Amit Naik, and thank you very much